Hi everyone, I am Dr. Kiran, working as an assistant professor in the Department of Electronics and Communication Engineering, MLR Institute of Technology, Hyderabad, India. Today we are going to do some exercise problems on diode current equation, then problems on the resistance of the diode, how to calculate the resistance of the diode, and what is the effect on temperature effect on current. Conclude with summary. Let us start the first exercise problem. Before going in detail, let us see. We know this is the conventional current equation. I is equal to I naught into e power v by eta vt minus 1. And please remember, for forward bias condition, we can neglect this one. And now we know all these parameters. Okay. And how to calculate the voltage equivalent temperature. So kT by Q, T by 11,600. At room temperature, it will be 26 millivolt. So all these are necessary for calculating the diode current equation. Let us start the first problem. So here we are given a silicon diode has a reverse saturation current of 7.12 nanoamperes. So given data, first write given data, that is reverse saturation current I naught is given 7.12 nanoamperes. Nanoamperes means 10 power minus 9 amperes. And at room temperature of 27 degrees centigrade. So just now we have told that 27 degrees means what? 27 degrees plus 273 degrees. If you add this becomes 300 Kelvin. So therefore at room temperature 300 Kelvin, Vt is equal to 26 millivolt. This we know. So what are the other parameters? We have given 0.7 volts. Calculate its forward current if it is forward biased with a voltage of 0.7 volts. So let us apply this. So we have to calculate forward current I, which is I into I naught into e power v by eta vt. So what is the value of eta here? So we are given silicon. So eta is equal to 2 for silicon, we know. Therefore let us substitute all the values. 7.12 into 10 power minus 9 e to the power v means what? 0.7 volts, 0.7 upon eta is 2 and Vt is 26 millivolt. So 26 into 10 power minus 3. So if you solve for this, so I am neglecting this minus 1 because in forward bias condition, so this value is more. So when compared with the minus 1, so we can neglect this one. So therefore, if you solve for this, you expect I is equal to approximately equal to 5 milliamperes. Reverse saturation current is 7.12 nanoamperes and actual diode current is 5 milliamperes. So this way, a simple calculation to calculate the diode current. So let us see the second problem. Here we are given a diode operating at 300 degree Kelvin at a forward voltage of 0.7 volts carries a current of 10 milliamperes. When the voltage is changed to 0.42 volts, the current becomes twice. Calculate the value of reverse saturation current and eta for the diode. So what we have to calculate? Reverse saturation current is what? And eta is what? Material constant is what? We have to calculate these two. So what are the given data we have? So that means two voltages, two different currents, right? So I naught is given. I naught is we need to calculate I naught. So with these two voltages, for example, V1 is equal to 0.4 volts. In such case, the current is 10 milliamperes. When V2 is equals to 0.42 volts, so V2, that means voltage applied to the diode is increased to 0.42 volts from 0.4 volt. Then what will be the current? Current twice. Current is twice means what? This is I1, this is I2. I2 becomes 10 I1, 2 I1, that is equal to 2 into 10 milliamperes. That is 20 milliamperes. So directly we can do this experiment. Example. So what we have to do? Let us write with these two voltages and currents. So let us say I1 is equal to I0 into e power V1 by eta Vt minus 1. I am not considering minus 1 because it is forward bias. So I don't consider minus 1. Similarly, I2 is equals to I0 into e power V2 by eta Vt. Okay. So here we have to calculate eta value and I0 value. So let us say this is first equation and this is second equation. So let us do 1 divided by 2. So what is I1 here? I1 is 10 milliamperes. 10 milliamperes upon what is I2? 20 milliamperes. That equals to I0 by I0 into e power V1 by eta Vt upon I0 into e power V2 by eta Vt. Here. So here 2 times it cancels out 2 times. So here now let us cross multiply this. So what we will get? I0 into I0 gets cancelled here. I0 gets cancelled. So if you cross multiply, you will get e power V2 by eta Vt is equals to 2 times, this 2 comes here, 2 times e power V1 by eta Vt. Okay. So now let us substitute the values of these. E power V2, what is the V2 value? 0.42 by eta Vt. So Vt value we know 26 millivolt, that equals to 2 into e power, what is the V1 value? 0.4 upon eta into 26 millivolt. Okay. If you solve for these values, so this is approximately, you will get a 15.38 upon eta, and this is 2 times e to the power 16.34 upon eta. Now to solve for this, let us apply natural logarithm on both sides. Natural logarithm on both sides. Okay. In such case, we can write this as, if you apply natural logarithm, it becomes 15.38 ln e to the power e is equals to, this is log m and log n, log m plus n. So this can be written as ln 2 plus, this can directly write 16.32 by eta is there, 16.34 by eta e to the power, so ln e to the base e. So this value is 1, ln e to the base e is 1. So therefore here what is the value of this ln 2? 0.63 something. Okay. If you take this outside, so that means 15.38, or otherwise you can write 16.34 by eta is equals to minus 15.38 eta. So which is equals to 0.63. So if you solve for this, then you will get the value, eta value becomes 1.10 something, which is equals to 1. So we know eta is equal to 1 means for, this is for germanium. Eta is equal to 1 for germanium. So this way you can, so we have calculated eta. Eta we have calculated. Now we have to calculate I0. So directly we can substitute in this. So first we have to calculate now I0. I0 is equal to I by eta Vt. So I value you can take any one, I1 or I2. So 0.4 I1 I take, and this one is 1 into 26 millivolt is the volt equivalent of temperature. So this is approximately, you will get 9.45 nanoamperes. So this way you can calculate the reverse saturation current and eta. Simple calculations. So let us do the third one. So calculate the dynamic forward and reverse resistance of a PN junction diode. So we have given silicon diode. So silicon indicates eta is equal to 2. When the applied voltage is 0.25 at a 300 degrees Kelvin and reverse saturation current is 2 microamperes. So here what we have to calculate? Dynamic resistance. So this is comes under finding the resistance value. So first of all, we know I is equal to I naught into e power v by eta Vt. So we know that another one, the relation between resistance and voltage, V is equal to IR. So resistance given by V upon I. Okay. So here we know that dynamic forward resistance means there is a change in the input voltage, accordingly your current also changes. So therefore, let us say differentiate with respect to voltage. Differentiate this equation, current equation with respect to voltage, then you will find di by dv is equals to, that means what? This is forward resistance, reciprocal of forward resistance, because V is equal, R is equal to V by I, but here it is di by dv. So we can write I naught into e power V by eta Vt into 1 by eta Vt. So differentiation for V by e power V by eta Vt means e power V by eta Vt into corresponding coefficient, that is 1 by eta Vt. So this is equals to I naught into e power V by eta Vt divided by eta Vt. So what is this? This we know. This is the actual current equation. So 1 by Rf is given by I by eta It Vt. So that implies reciprocal forward resistance can be written as Rf is equals to eta Vt by I. Simple. By neglecting minus 1, because in forward bias the e power value is more. Okay. So if you know the eta value, if you know the volt equivalent of temperature and current flowing through the diode, then you have to calculate, you can easily calculate the forward resistance of the diode. Similarly, here Rf can be written as Vt by I is what? I naught into e power plus V by eta Vt we have written. Whereas in contrast, in reverse direction, that is reverse resistance, in reverse bias direction you have to write eta Vt by I naught into e power minus V by eta Vt. These two are very, very important. So for calculating these diode resistances forward, in forward and reverse directions, you have to use only, simply you have to change the polarity of the input voltage. Here in forward direction you have to use plus V, here you have to use minus V. That's it. Okay. So now let us do this problem. So what are the given data we have? Dynamic forward resistance we have to calculate, and reverse resistance. Both dynamic forward resistance and reverse resistance we have to calculate. Silicon diode, when the applied voltage is 0.25 volts. Applied voltage V is given 0.25 volts and the temperature T is equal to 300 degree Kelvin. So that implies what? Volt equivalent of temperature is 26 millivolt. And reverse saturation current I naught is given. I naught is 2 microamperes. So with this data, let us calculate the dynamic forward resistance. What is the dynamic forward resistance? Rf is equals to eta Vt by I. That is equal to, eta is 26 into 10 power minus 3 volts upon into Vt value is 26 millivolt. So what kind of type semiconductor is silicon? So silicon means what? 2. So eta value is 2. So it is 2 into 26 by upon I is equal to I naught. I naught value anta? what is the value of I naught? I naught value is given 2 microamperes. 2 into 10 power minus, micro means what? 6. 2 microamperes. I naught into e power v. V value is 0.25 upon, what is the value of e power plus v by eta vt. Eta means what? 2 into 26 millivolt. So if you solve for this, the RF value becomes approximately 212.337 ohms. So this is the forward resistance. So forward resistance is less compared to reverse resistance. That we'll see. Then only current is flowing through the diode. So in the second case, reverse resistance. In reverse resistance, RR is given by eta Vt by I. I means I naught into e power minus V by eta Vt. That is equal to 2 into 26 into 10 power minus 3 upon 2 into 10 power minus 6 e to the power minus 0.25. Here we have to use V minus value. Input applied voltage minus voltage. So minus 0.25 by 2 into 26 into 10 power minus 3. So this gives you approximately 3.18 mega ohm. So please compare these two values. Forward resistance. In forward resistance, the resistance is 212 ohms only. Whereas reverse resistance 3.18 mega ohm. That means in reverse direction, reverse bias condition, obviously there is no current flow. So it has large resistance. Okay. So in this way you can calculate the resistance of a diode. Let us see another one. A PN germanium diode has a reverse saturation current. So we are given I naught, reverse saturation current 30 microamperes at a temperature of 125 degrees centigrade. 125 degrees centigrade, temperature is 125 degrees centigrade. Okay. So you need to change this into Kelvin. So Kelvin means what? 125 degrees centigrade plus 273 degrees centigrade. Of course, it becomes 300 Kelvin, approximately 398. Approximately 398 Kelvin. Okay. So if you use in this equation, Vt is equal to T by 11,600. So it will be 398 by 11,600 is approximately equal to 34.3 millivolt. You can check this. So if you solve for this, you will get this value. And similarly, so we have to calculate what? Dynamic resistance. Okay. At the same temperature, you have to calculate the dynamic resistance. So RF, first you have to calculate forward resistance. Then we can also calculate the reverse resistance. So eta Vt by same I into I naught into e power plus V by eta Vt. In this way, you can calculate. Similarly, RF is equals to eta Vt by I naught into e power minus V by eta Vt. So with this way you can calculate. This value becomes 3.3561 ohms and this is approximately 389.49 kilo ohms. Okay. So this is the procedure how to calculate the resistance, forward resistance and reverse resistance of a diode. Okay. I'll stop here. So we'll continue in the next session.